Hello, my name is Julio. This is my individual PowerPoint presentation for the class CIVE 6324, Construction Methods and Equipment. My PowerPoint topic is on a step towards autonomous construction projects in the field of construction industry of road projects. Now, how do we conduct smart road construction projects? And what do we define by smart in these projects? Well, the following research talks about a smart site, and it attempts to tackle some of the questions and some of the complications involved with these procedures. A smart site is a research project that incorporates decision theory, machine learning, and distributed artificial intelligence to design and test multi-agent systems, MAS, for asphalt road construction. Smart Site incorporates sensing and communication technologies which can integrate real-time automated information exchange in the supply chain of road construction. A real-time path planning system is introduced for compactors and presents the results of several simulations and field realistic experiments conducted to evaluate the system in a harsh construction environment. The usage of Smart Site can benefit asphalt compactor operators, allowing them for better control of their machinery based on environmental, material-related, and process-related disturbances or changes. This process can improve the quality of the delivery and laying of asphalt material, prevents compactors from over-compacting certain road segments, increases the road's pavement longevity during the operational life cycle, refocuses the work tasks of site managers, and reduces the construction budget and schedule of the project. This system makes it an important step towards the development of fully automated asphalt compactors. Well, let's start by first determining what are some of the problems that are in the road construction industry. What are some of the problems that we have there. And well, let's start with this excerpt right here. The European construction industry contributes nearly 10% of the EU GDP, but close to 90% of its projects suffer from budget overruns or delays. Majority of the time, this is due to inadequate planning and management. The asphalt compaction process itself is one of the most important steps in road construction. And of course, fixing the quality of these defects can be both time and money consuming. Now, what are some of the key factors that we gotta look in for during the compaction process? Of course, the main factors are the environmental preconditions and the material properties. Now, we put a lot of emphasis on the compaction process because, well, what is the importance of the compaction itself? Well, in order to have good asphalt quality, the compaction process is a very critical step in order to achieve the best possible service and ensure the standard of the road that you're going to be putting. Some regular problems that keep us from achieving this necessary quality include things such as inappropriate number of passes, which itself leads to over or under compaction, too low core temperatures, which can lead to under compaction or damage to the asphalt layer, or too hot temperatures, which can lead to the liquid components to be pressed out and create subsidence. Well then, what do we need to watch out for? What do we need to do then to avoid this? In order to avoid this, we have to have the right number of passes within the right temperature range, taking into consideration the influence that environmental and material-related conditions have on the crucial factor of the quality required. Now, human error is at times inevitable, and human operators are not supported by adequate assistance systems. Sure, the usage of GPS has been used and implemented within the machinery equipment and has been used for support by machine operators. But the focus of these market available solutions is to provide data about temperature and compactor for documentation purposes after the construction process, instead of supporting the operators during compaction. Right now, there is a need for real-time integrated control systems to support human machine drivers at an operational level during compaction. Now, what are multi-agent systems? These are agents that can communicate with each other in order to coordinate and cooperate, being able to perform actions via its actuators, and the action itself being able to be manipulated in the physical world or through a virtual or digital action like a screen. Value chains to be addressed include the field of construction machines, site environment, connected work site, as well as construction process monitoring. The Smart Site platform brings together these interdependent and interacting value chains. And again, these value chains, of course, come from the field of construction machines, site environment, and the data that is collected from these fields, of course, includes data for every machine along the entire value chain. This data can, of course, therefore be used in project management by the end users, such as project consultants and general contractors. When talking about the logistics chain of blacktop assembly or hot mix asphalt, of course, we have to talk about the batch plants, transportation facilities, pavers, and of course, compactors. Now, what can SmartSite improve here in the equipment, machine, and plant innovations of batch plants? Well, right now with current asphalt plants are not sufficiently integrated into road construction information systems. As such, the integration of the batch plants into the systems become a matter of solving the bottleneck in the optimization of the construction site, since deliveries cannot be adjusted based on as-built information. This process can therefore reduce time spent at the plant for each truck and allow for the dynamic adjustment of delivery times. Now, in the process of logistics, of course, in road construction, the coordination of logistics is lacking, and utilizing live vehicle tracking for each truck for the asphalt deliveries can be monitored and coordinated. The integration of paver and batch plants can enable just-in-time scheduling of asphalt deliveries, which allows for fewer dump trucks to be necessary. At the moment, we don't have fully autonomous pavers yet. But of course, with the innovations that are created through the usage of SmartSite, we can create, right now, we can improve the life cycle of asphalt road construction through the usage of intelligence assistance for compactor operators. The first simulation we have for the usage of SmartSite involved using turning conditions using designed agents steering recommendations with the same interface a human operator would use to steer a regular compactor. The results from this experiment concluded in the following. Experiment results favored medium length compactions with maximum compaction lengths of 20 meters to 30 meters, resulting in poor values. While very long compaction paths of 50 meters produce unnecessarily high pass counts, but also increase the variance in pass count. In this table, we have the results that were acquired from the maximum compaction path lengths, as well as the compaction measurements, compaction equivalent, standard deviations, average passes, and more information. Simulation 2 involved using aligned paths characterized with synchronized turning points for one set of compaction paths, while rotors using non-aligned pathing always closely follow the paper. Now, in this simulation, we have a comparison between aligned paths and non-aligned paths, with all other factors being identical. As we can see here, the darker area represents the more, the darker the area is, the more compacted the area is. Here we have the results for the path aligning, and as we can see here, for short path lengths of 20 meters and 20 meters, the achieved compaction of 10 or more compactions improves significantly to almost 100%. The third simulation consisted of testing the influence of varying paver speeds, where the results showed that for varying paver speed, with active path aligning, the compaction quality suffers when the speed deviates from the optimum in either direction, whether it be the paver speed being too slow, the paver speed being too slow, or the paver speed being too high. We can see here that if it was too slow, the amount of passes and the compaction equivalent increases, as well as a standard deviation. Not only that, this increases the risk of overcompaction. While at the same time, if the paver speed was too high, there is a large increase of undercompacted areas. Now, with the last simulation being simulation 4, this involved doing a preliminary field trial that assessed the functionality of the system under outdoor environmental conditions. Here, during the testing, the operator was able to recognize and follow target paths and was easily available, or better said, easily able to adapt to the system even with no prior training. But the problem with this is that we need more usability studies in order for us to deploy the system. Aside from that, we also have to realize the limitations of the smart system, which of course the limitations of the system include that it is highly dependent on the availability of GPS tracking and network connection in order to facilitate the data transfer between our components, the multiple components. Not only that, but a loss of network or GPS can blind our machines, which will limit the applications of this automated compaction. High accuracy GPS is required in order to ensure the compaction quality of this system. The proposed system itself, when used with and followed by human compactor operators, does lead to high quality compaction results. And here is my works cited, of course, for the smart site research. This is the end of my presentation. Thank you very much.